we have proved mathematically that information tends to leak in a cascade of information channels. We have also found necessary and sufficient condition that a cascade not lose information. We will extend this result to see how to obtain a reduced set of channel outputs without loss in information. For example, in a case of binary data transmission by satellite, the output received at the earth station often contains irrelevant information the antenna on the earth in such a system might obtain a sequence of pulses of various amplitude. The receiver would take each pulse and compare it with a threshold. If the amplitude of the pulse is larger than the threshold, it converts that pulse to a binary 1, and if it is below the threshold, it converts the pulse to a binary 0. We may think of two channels in the situation just described. First, there is a channel with a binary input that is sent from the satellite and a large number of outputs corresponding to the number of distinguishable pulse amplitude. Second, we could think of a channel with a binary inputs and binary outputs corresponding to the outputs of a receiver. Now, this second channel is clearly a simplification of the first channel. We call the second channel as a reduction of the first channel. So, let us define the reduction of a channel. So, consider channel with R inputs and S outputs, and this channel is described by a channel matrix P of the form P11, P12, P1I, P1I plus 1, P1S. Similarly, we have P21, P22, P2I, P2I plus 1, P2S, PR1, PR2, PRI, PRI plus 1, PRS. Given this channel matrix, we define a new channel with R inputs and S minus 1 outputs by adding together any two columns of this matrix P. We could combine the ith column and I plus 1 column to get a reduced set of outputs. So, when we do this kind of combination, we call the channel matrix of the new channel P dash, and that is equal to P11, P12, P1I plus P1I plus 1, P1S, P21, P22, P2I plus P2I plus 1, P2S, PR1, PR2, PRI plus P r I plus 1 P r s. So, this channel matrix of the new channel P dash, the new channel P dash is called an elementary reduction of P. Now, we may repeat this process of combining a number of times, each time forming an elementary reduction of P dash. So, the end product of more than one elementary reduction will be simply called a reduction of the original channel matrix P. So, let us illustrate this with an example. So, let us take a case of a second extension of a binary symmetric channel, for which the channel matrix we have seen earlier is of the form P bar squared P bar P P P bar P squared P bar P P bar squared P squared P P bar P P bar P squared P bar squared P bar P P squared P P bar P bar P P bar squared. So, this is a channel matrix for the second extension of a binary symmetric channel. So, an elementary reduction of P is formed by combining the first and second column of this matrix, and if we do that, we will get as P dash is equal to P bar P P bar P squared P bar P squared P bar P P bar squared P bar P, and finally P P bar P and P bar squared. Now, a reduction of P is formed by combining the second and third column of P dash. So, if we combine second and third column of P dash, we will get a reduction of P, which will denote by P double bar equal to P bar P P bar P P P bar P B bar. A useful way of viewing a reduced channel is as shown in the figure here. So, I have a channel matrix B, I take its output and feed it to a deterministic channel. The input of this is A, the output is B, and the output of this is C, and this is reduced channel. So, the deterministic channel combines symbols of the B alphabet into a smaller number of symbols of the C alphabet. Hence, the channel with the input alphabet A and output alphabet C indicated by dashed lines in this figure is a reduction of channel P. Now, this method of constructing a reduced channel allows us to use the results which we had discussed in the last class on channel cascades. So, in particular we have, with reference to what we had studied in the last class, with reference to this figure, we can say H of A given C is greater than or equal to H of A given B, and I of A colon C is less than I of A B. So, forming a reduction of a channel decreases or at best leaves unchanged the mutual information of the input and output alphabet. Now, this is the price we pay for simplification in the channel. Now, a most important question suggested by the above remark is, when can we simplify the channel without paying a penalty in reduced mutual information? That is, when is the mutual information of a reduced channel equal to that of the original channel? So, in order to answer this question, we need only consider the case of elementary reductions. The question in the case of a general reduction may then be answered by induction. So, let us form an elementary reduction of the channel P, which is given by P11, P12 up to P1s, P21, P22, P2s, PR1, PR2, PRs. Now, without loss of generality, we may assume that the elementary reduction of this channel matrix P is formed by combining the first two columns of P. Now, if we assume this, then the channel diagram these are the input alphabets, and so this is the alphabet B and this is the alphabet C. So, A, B and C. So, this is the channel reduction by cascade. Now, we found necessary and sufficient condition that a cascade not lose information. Let us rewrite that condition. The condition said that probability of A given B is equal to probability of A given C. This is true for all A, B and C symbols such that probability of B, C is not equal to 0. Now, since we are investigating an elementary reduction, this condition is satisfied trivially for all B symbols except the two symbols we have combined, B1 and B2. So, these two symbols we have combined here, this is B1 and this is B2. So, and in this figure this is your C1. So, on applying this condition to B1 and B2, we find the necessary and sufficient conditions for cascade not to lose information is probability of A given B1 is equal to probability of A given C1 is equal to probability of A given B2. This condition should be true for all A. Now, let us look at what is probability of A given B1 and probability of A given B2. Probability of A given B1 is equal to probability of B1 given A multiplied by probability of A upon probability of B1, and probability of A given B2 is equal to probability of B2 given A multiplied by probability of A upon probability of B2. So, and probability of A given C1 is equal to probability of C1 given A probability of A whole over probability of C1. Now, this expression can be rewritten as probability of C1 given B1 probability of B1 given A plus probability of C1 given B2 multiplied by probability of B2 given A probability of C1 given probability of C1 is equal to probability of C1 given B1 multiplied by probability of B1 plus probability of C1 given B2 multiplied by probability B2. Now, because the output B is fed to the deterministic channel whose output is C alphabet, what it implies probability of C1 given B1 and probability of C1 given B2 are both equal to 1. So, in that case this simplifies to probability of B1 given A plus probability of B2 given A, probability of A divided by probability of B1 plus probability of B2. Now, what this implies is that if these two conditions are satisfied, then it implies that probability of A1 of probability of A given B1 equal to probability of A given B2 is also equal to probability of A given C1 from this and this condition. So, this condition is equivalent probability of A given B1 equal to probability of A given B2 for all A. In other words, the two output symbols B1 and B2 may be combined without loss of information if and only if the backward probabilities, that is probability of A given B1 is equal to probability of A given B2 for all A. Now, this is an important result both in terms of understanding information and from a practical point of view. It provides condition under which a channel may be simplified without paying a penalty. The backward probabilities, however, depend upon the a priori probabilities PAI, that is, they depend upon how we use our channel. So, it is of even more interest to determine when we may combine channel outputs no matter how we use the channel, that is for any a priori probabilities P of AI. So, in order to get the answer for that, let us use Bayes' rule to rewrite this expression. So, this expression may be rewritten using Bayes' rule as probability of B1 given A multiplied by probability of A divided by summation of probability of B1 given A probability of A. This will give you probability of B1 is equal to probability of B2 given A multiplied by probability of A whole over summation probability of B2 given A multiplied by probability of A. This condition should be valid for all A. So, this can be simplified as probability of B1 given A upon probability of B2 given A should be equal to summation probability of B1 given A multiplied by probability of A upon probability of B2 given A probability of A. This should be valid for all A. Now, if this condition is to hold for all possible a priori probabilities PAI, then what it implies that probability of B1 given A should be equal to constant times probability of B2 given A for all A. So, this is the condition we seek. So, if you have a channel matrix satisfying this condition, we may combine two columns of the matrix and the new channel matrix will be as good as the original one. So, more precisely, for any set of probabilities over the input alphabet, the mutual information of the channel and the reduced channel will be identical. So, a reduced channel with this property will be called a sufficient reduction. An example of this would be a channel with a channel matrix given as 1/6, 1/3, half, 0, 1/12, 1/6, 1/4, half. Now, this may be reduced to half, half, 0, 1/4, 1/4, half, because this column is half the times this column, and this may be finally reduced to, by combining these two columns, as 1, 0, half, half. So, this is a sufficient reduction of the original channel. Now, another important property of mutual information is additivity. We will investigate additivity by considering the average amount of information provided about a set of input symbols by a succession of output symbols. That is, we consider the case where we may gain information about the input by a number of observations. That is, we consider a case where we may gain information about the input by a number of observations instead of a single observation. An example of this situation occurs when the input symbols of a noisy channels are repeated at a number of times rather than transmitted just once. Such a procedure might be used to improve the reliability of information transmitted through an unreliable channel. Another example is an information channel where the response of a single input is a sequence of output symbols rather than a single output symbols. So, let us investigate the additive property of mutual information in the special case where the output of a single input symbol consists of two symbols. The more general case where the output consists of n symbols may then be treated by induction. So, let us modify a model of the information channel then so that instead of a single output for each input, we receive two symbols, say Bj and Ck. The symbols Bj and Ck are from the output alphabets B equal to Bj, where J goes from 1 to S, and Ck is from the output alphabet C equal to K equal to 1, 2 up to T. So, without loss of generality, we may assume that the two output symbols are received in the order Bj followed by Ck. So, then the a priori probability of the input symbols Pai change into the a posteriori probability P of AI given Bj upon reception of the first output symbol Bj, upon reception of the second output symbol Ck, they change into the even more upper posterior probabilities, that is probability of AI given Bj Ck. So, if the two symbols Bj and Ck are received, the average uncertainty or entropy of the set of input symbols changes from Ha equal to Pa log 1 by Pa to the a posteriori entropy given by H of A Bi to H of A given Bj equal to probability of A given Bj log of 1 by probability of A given Bj. This summation is over input alphabet A, and on receiving Ck, this a priori entropy changes to the even more a posterior entropy, which is given by H of A given Bj Ck equal to probability of A given Bj Ck log of 1 by probability A given Bj Ck. The summation is over A. So, now if we average this quantity over the Bj to find the average a posteriori entropy, we will get the equivocation of A with respect to B. So, probability of B H of A given B averaged over B alphabet will give us equivocation of A with respect to B, that is H of A given B. So, in the same manner we may average this term over all Bj and Ck in order to find the equivocation of A with respect to the output alphabet B and C. So, if we do that, we get the quantity as follows. And this is by definition equivocation of A given B and C. So, the results of our generalization of Shannon's first theorem applies directly to this term. So, this quantity is the average number of bits necessary to encode a symbol from the alphabet A after we are given the corresponding B and C symbols. Now, this equation and this equation out here suggests two different ways we might measure the amount of information B and C yield about A, that is the mutual information of B, C and A. So, we can define the mutual information of A and B C just as we did in the case when the channel output consisted of a single channel. So, that is mutual information between A and B C is by definition we can say equal to H of A minus H of A given B C. This is one way of defining. Second way of looking at the same thing is to consider the amount of information provided by A. The second way is to consider the amount of information provided about A by B alone, and then the amount of information about A provided by C after we have seen B. So, let us look at these quantities. So, we have the quantities of the type H A minus H of A given B and H of A given B minus H of A given B C. Now, this first quantity has already been defined, and that is nothing but mutual information between A and B. So, now it is natural to define this quantity as mutual information of A and C given B. So, if we add this equation and this equation, we find I A B plus I A colon C given B is equal to H A minus H of A given B C, and that is equal to mutual information between A and B C. So, what this expression expresses is that, so this equation expresses the additivity property of mutual information. It says that the average information provided by an observation does not depend upon whether we consider observation in its entirety or broken into component parts. So, this equation may be generalized immediately to more than one variables. So, this equation can be generalized as follows: I of A and B C D equal to I of A B plus I of A C given B plus I of A D given B C. Now, in this equation, the first term on the left is the average amount of information about A provided by an observation. Now, in this equation, the term on the left is the average amount of information about A provided by an observation from the alphabets B, C dash dash up to D. The first term on the right is the average amount of information about A provided by an observation from the alphabet B. The second term on the right is the average amount of information about A provided by an observation from the alphabet C after an observation from the alphabet B, and this term is the average amount of information about A provided by an observation from the alphabet D after an observation from the alphabets B, C dash dash. So, it is important to also realize that the particular order of the information we receive is irrelevant. Now, if we look at this two equation, it clearly shows that a particular order of the information we receive is irrelevant. For example, we may write this equation as mutual information between A and B C is equal to mutual information between A and C plus mutual information between A and B given C. Now, we may write the information quantities discussed in several different forms. For example, I of A, B, C, which is written as H A minus H of A given B C is equal to probability of A log 1 by probability of A summation over alphabet A minus this by definition is equal to probability of A B C log of 1 by probability A given B C, the summation over A B C alphabets. Now, this can be rewritten as probability of A B C log 1 by P A summation over A B C alphabet. This quantity is again repeated probability of A B C log of 1 by probability of A given B C, and this can be simplified as probability A B C log of probability A given B C divided by probability of A summation over A B C. Now, another useful form which is found by multiplying the numerator and denominator of the log term in this equation is by probability B C. So, if you multiply both terms by probability B C, we get I of A colon B C equal to probability of A B C log of probability A B C divided by probability of A multiplied by probability of B C summed over A B C. Now, the similarity of this equation and this equation is very clear if we compare to what we had done earlier. I of A B is equal to probability of A B log of probability A given B upon probability of A summed over A B. So, this expression or this equation is similar to this equation, and I of A colon B is equal to probability of A B log of probability A B upon probability A probability B summed over A B alphabet, and this is similar to this. So, what it implies that we could have obtained this equation and this equation by replacing B by B C. So, if we go by this argument, then we can define H of B C given A equal to probability of A B C log of 1 by probability B C given A summed over A B C. So, we can, using this relationship, it is easily verified that mutual information between input alphabet A and output alphabet B C is equal to H of B C minus H of B C given A. We will illustrate the additivity property of mutual information by examining example based on a binary symmetric channel. This we will do in the next class. In the next class, we will also extend our definition of mutual information to more than 2 alphabets. We will also investigate an interesting property of information channel, that is channel capacity. We know to calculate the mutual information of a channel, it is necessary for us to know the a priori probabilities of the input alphabets, that is PAI. So, what it implies that calculation of mutual information for a channel not only depends on the channel matrix, but also on the a priori probabilities PAI, that is on how we use the channel. So, it is of interest to see how the mutual information varies with this PAI and what is the maximum value which we can achieve, and this maximum value is defined as channel capacity. We will investigate this in the next class.